Combinatorics, Lecture 19, Old Examinations. So this will be solution to the problems given on examination in combinatorics from the 12th of March 2010. Problem 1. What is the probability that a standard poker hand has two pairs? Explanation. A standard poker hand consists of 5 cards drawn randomly from a standard pack of 52 cards. Two pairs means that the hand has two distinct pairs of cards of the same rank, and these are two different ranks. And there is one additional card of a different rank, that's the third rank. Solution. For this problem, the sample space omega consists of all possible ways to select 5 cards out of 52 cards. This can be done in 52 choose 5 different ways, so the cardinality of omega is 52 choose 5. So let A be the random event that the hand has two pairs. To construct such a hand, we can proceed as follows. First, we choose two different ranks for the pairs. There are 13 ranks, so we can choose two different ranks out of 13 in 13 choose 2 different ways. Second, we choose 2 cards for one of these ranks. So there are 4 cards of a given rank, we choose 2, that's 4 choose 2 different ways. And similarly, we choose 2 cards for the other of these 2 ranks, also in 4 choose 2 different ways. Finally, the remaining card can be chosen in 44 different ways. That's because we have 52 cards in total and 2 ranks, which means 8 cards are now prohibited. What remains is 1 out of 44 remaining cards, so we can do it in 44 different ways. And these steps are independent in the sense that the number of ways to make a step doesn't depend on the outcome of the previous steps. So by the rule of product, the cardinality of our random event equals 44 times 13 choose 2 times 4 choose 2 times 4 choose 2. And this gives us the following answer. The probability that a randomly chosen hand of 5 cards for poker, that this hand has 2 pairs, is the fraction where the numerator is 44 times 13 choose 2 times 4 choose 2 times 4 choose 2, and the denominator is 52 choose 5. One can compute that the approximate value of this is approximately 0.04754 and so on. Problem 2. Formulate the rule of product. How many words of length 9 can one construct using 1 letter K, 3 letters S, 2 letters T, and any, possibly repeating 3 vowels, that is, letters from the set A, E, I, O, and U? Solution. The set theoretic version of the rule of product is as follows. If X and Y are finite sets, and X times Y is their Cartesian product, that the set of all pairs A, B, where A is in X and B is in Y, then the cardinality of this Cartesian product equals the product of the cardinalities of X and Y. The combinatorial formulation of the rule of product is usually as follows. If some process or experiment consists of 2 successive actions, where the first action can be done in K different ways, and the second action can be done in M different ways independently of the outcome of the first action, then there are in total K times M different possible outcomes of this process or experiment. And one can generalize it to several actions, not necessarily 2. So if there are R consecutive independent actions, where the ith one can be done in Ki different ways, then the total number of ways to perform them all, one after other, is K1 times K2 times and so on times Kr. Now to our problem with words. So we want to find out how many words can one construct using 1 letter K, 3 letters C, 2 letters T, and 3 vowels. We can repeat the vowels if you wish, and the vowels are letters from the set A, E, I, O, and U. So to construct such a word, what we can do is the following. First, we choose the place for the letter K. We have 9 places, we need to choose one. That's 9 choose 1, that is 9 different ways. Second, we have 8 places left. We choose 3 places for S's. 8 choose 3 different ways. So that's in how many ways we can do action 2. Now action 3. We have 5 places left. We choose 2 places for 2 letters T. We can do this in 5 choose 2 different ways. What remains is 3 places, and each of them can have any vowel. So we need to choose one of 5 vowels, we can repeat them, for each of the remaining 3 places. So for each place we have 5 choices. So by the rule of product, the answer will be 9 times 8 choose 3 times 5 choose 2 times 5 to the power 3. That is the answer to problem 2. Problem 3. N dice are rolled at the same time. What is the probability that all numbers from 1 to 6 show up if A. n is equal to 3, B. n is equal to 6, and C. n is equal to 9? Solution. The sample space omega here consists of all possible outcomes of rolling n dice. Since each single die outputs one of the 6 numbers 1, 2, 3, 4, 5, 6, by the rule of product, the cardinality of omega is 6 to the power n. Let x be the event that all numbers from 1 to 6 showed up. If n is equal to 3, then x is empty because we cannot have 6 numbers when we only have 3 dices. Therefore, in this case, the probability of x is 0, that's the answer to part A. If n is equal to 6, then each number shows up exactly once, so x consists of all permutations of 6 elements. So we just need to find out on which dice each number shows up. So the cardinality of x is 6 factorial, so the probability of x is 6 factorial divided by 6 to the power 6. This is the answer to problem B. One can note that this is approximately 0.01543. Now, if n is equal to 9, then in order to solve the problem, it is convenient to view elements of x as functions from the set of all dice, we have 9 dice, to the set of the outputs 1, 2, 3, 4, 5, 6, the numbers which we get when we roll a die. So the condition that all numbers show up correspond to the notion of a surjective function. So the cardinality of x equals the number of surjective functions from a set with 9 elements to a set with 6 elements. And there is an explicit formula for this, that's a sum over all k from 0 to 6, and then the summand is minus 1 to the power k, 6 choose k, times 6 minus k to the power 9. So the answer to our problem for n is equal to 9 is that the probability of x is this sum over all k from 0 to 6, minus 1 to the power k, 6 choose k, 6 minus k to the power 9, divided by 6 to the power 9. One can compute that this is approximately 0.189, so approximately 0.2. That's the answer to part C. Problem 4. Find a formula for an, where n is greater than or equal to 0, satisfying an is equal to 2an minus 1 plus 3an minus 2 for all n greater than or equal to 2, with the initial conditions a0 is equal to a1 is equal to 1. This is an example of a homogeneous linear recurrence with constant coefficients. So we write the characteristic polynomial, that's x squared minus 2x minus 3. It has roots minus 1 and 3. So the general solution to the recurrence is given by an is equal to alpha times minus 1 to the power n plus beta times 3 to the power n for n greater than or equal to 0, where alpha and beta are some numbers. So to determine alpha and beta for our particular sequence an, we use the initial conditions. So for n is equal to 0, we get 1 is equal to alpha plus beta. And for n is equal to 1, we get 1 is equal to minus alpha plus 3 beta. If we add the two equations, we get 2 is equal to 4 beta, which gives us that beta is 1/2. And from the first equation, alpha is equal to 1 minus beta. Since beta is 1/2, it follows that alpha is also 1/2. And now we can write the answers that an is equal to minus 1 to the power n plus 3 to the power n divided by 2. And this is true for all n greater than or equal to 0. Problem 5. Two teams took part in the final of the Uppsala Academic Festival. The 121 incoming telephone votes were distributed as follows. Team 1 got 60 votes and Team 2 got 61 votes. And these votes were counted live, one by one, by a local TV station. A. What is the total number of the possible sequences of such votes? B. What is the number of the possible sequences of such votes which satisfy the condition that Team 2 was in the strict lead from start to finish? So these problems actually on the examination were given as two separate problems, but I combined them as one problem. Solution. To answer A, we need to find a number of sequences of length 121, where each term of the sequence is either 1 or 2. So it's a vote for Team 1 or vote for Team 2. And such a sequence should have exactly 60 entries which are equal to 1. By the definition of the binomial coefficient, the number of such sequences is 121 choose 60. We need to choose 60 places for 1 out of 121. And this answers problem A. To answer part B, we need to find the number of such sequences. So sequence length 121, each entry is either 1 or 2, but such that Team 2 leads all the way. So the condition for the sequence is that in each non-empty prefix, the number of 2's is strictly greater than the number of 1's. So in particular, such a sequence must start with a 2. And then we have a condition that if we delete this 2, the remaining sequence has length 120, it has 60 1's and 60 2's, and it satisfies the condition that each prefix contains at least as many 2's as 1's. But then the number of such sequences is exactly the Catalan's number C60 by the definition of the Catalan number, and C60 is a number which can be described as 1 divided by 61 times 120 choose 60. This answers problem 5. Problem 6. The government has decided to create and distribute n new PhD positions among 5 different universities. For political reasons, the distribution must satisfy the following conditions. A. Each of the universities should get at least 1 position. B. Uppsala should get at least 3 positions. C. Lund and Umeå should get at least 2 positions each. D. Göteborg should get at most 3 positions. And E. Stockholm should get an even number of positions. Determine the generating function for the number an of ways to make such a distribution, so it depends on n, and compute A10. Solution. We can interpret our an as the number of positive solutions to the equation r1 plus r2 plus r3 plus r4 plus r5 is equal to n, which satisfy the condition that r1 is greater than or equal to 3. This corresponds to Uppsala. R2 and R3 are greater than or equal to 2. This corresponds to Lund and Umeå. R4 is less than or equal to 3. That's Gothenburg. And R5 is even. That's Stockholm. Then our summoned R1 should correspond for the generating function to the factor x to the power 3 plus x to the power 4 plus and so on. So the exponents here are all possible solutions for R1. We take the sum of them, and we can rewrite the sum as x to the power 3 times the usual geometric progression, 1 plus x squared and so on, which we can write as 1 divided by 1 minus x. So the factor which corresponds to R1 in the generating function is x to the power 3 divided by 1 minus x. For R2 and R3, we have similar factors, but they should start from x to the power 2 because R2 and R3 can be 2, 3, and so on. So the corresponding factor should be x to the power 2 divided by 1 minus x. For R4, possible solutions are 1, 2, and 3 possible values in the solution. So R4 should correspond to x plus x squared plus x to the power 3. And R5 should correspond to even powers of x. So it's x to the power 2 plus x to the power 4 plus and so on. And this we can write as x squared divided by 1 minus x squared. So now we multiply all this and we get the following generating function. X to the power 3 divided by 1 minus x times x squared divided by 1 minus x times x squared divided by 1 minus x times x plus x squared plus x to the power 3 times x squared divided by 1 minus x squared. We can rewrite it actually as x to the power 9 times x plus x squared plus x cubed divided by 1 minus x to the power 4 times 1 plus x, or even as x to the power 10 times 1 plus x squared divided by 1 minus x to the power 4 times 1 plus x. So this is our generating function. And from this expression, we immediately see that the coefficient at x to the power 10 is actually 1. And in fact, the whole generating function starts from x to the power 10. So we have here x to the power 10 factor. Then we have some polynomial with free coefficient 1. And then we have divided by, so the rest is given by the geometric series, which also have coefficient 1 as the free term. So this means, in particular, that a10, the coefficient at x to the power 10, will be equal to 1. Problem 7. 10 kids want to swing on a big seesaw with a lot of place for several kids on each side. Assume that each kid weighs between 5 and 100 kilograms. Prove that it is always possible to select two groups consisting of one or more kids each. The total amount of kids in these groups can be less than 10, such that the weights of the two groups are the same if rounded up to the closest integer amount of kilograms, so that they can swing together in balance, one group on each side of the seesaw. Solution. There are 2 to the power 10 minus 1, which is 1023 non-empty groups of kids. Each group has the total weight of 5 to 1000 kilograms. So one kid has a minimal weight of 5, and 10 kids per 100 kilograms have the maximal weight of 1000 kilograms. By the pigeonhole principle, there are two non-empty groups of kids with the same weight. Of course, these two groups might have a non-empty intersection. However, since each kid weighs more than 1 kilogram, none of these groups can be a subgroup of the other one. Therefore, we can remove the intersection and we get two disjoint groups of kids with the same weight. And this completes the proof of problem 7. Additional problems and questions at the end. Problem question 1. 12 dice are rolled. What is the probability that each number 1, 2, 3, 4, 5, 6 will show up exactly twice? Problem question 2. Determine the generating function for the sequence an is equal to 1 divided by n plus 1 for n greater than or equal to 0. Problem question 3. Determine the exponential generating function for the same sequence. Problem question 4. One randomly chooses 13 cards out of 52. What is the probability that each rank is represented? And problem question 5. How many words of length 10 can one form using the letters A, B, C, and D, such that each letter is used at least once? Thank you very much, and see you next time.